So today we're going to take a bit of a different tack. I know we were working on, yeah, I know, I apologize. Hey, hey, Holly, or Tyler, sorry, Tyler. Hey, Sam, and you were totally correct, Liam. It, I'm, I'm going to get better at that, I promise. It's just every time I see it, my first response is to go, Holly, and then I go, no, Tyler. It'll get there. It'll get there. At the very least, I'll be able to correct myself. Yeah, I know it says Arduino here. Unfortunately, we're not going to be working with Arduino because I know that not everybody's going to have a SparkFun kit. Um, what this is actually more for is to, I know, a lot of sad faces. This is more for 123D Circuit because we're going to start doing some stuff with 123D Circuit. We're actually going to learn how to make circuits on it, and then we're going to move on to learning how to make printed circuit boards with 123D Circuit. Because I know you guys, when you do lab and stuff like that, you're going to be messing around with the CNC machines. And one of the things that CNC machines can make are printed circuit boards. And those are pretty cool. Basically, they're just, you don't have to actually download 123D Circuit. It's online entirely. So it's just a thing that you run through, generally through Google Chrome. And yeah, makes it a lot easier. Um, but yeah, the entire point is to get used to that, to learn how to design circuits and stuff like that. Oh, yes, I should explain. CNC, 3 letters, stands for Computer Numerical Control. Basically, it is a computer-controlled machine that does cuts and milling and stuff like that. Um, but yeah, you guys might have some experience with CNC machines in the future in lab. So that's part of what we've actually been working with. So like Mesh Mixer and Tinkercad and stuff like that. Those are things that can be used for CNC machines um, in order to, get to make something with them. But basically, let me pull up a picture of a CNC machine real quick. There's a whole bunch of different kinds of CNC machines. The one that you guys would end up using would probably look something like. Let me just go ahead and open image in new tab. There we go. And we'll open this image in a new tab as well. But the one that you guys would be using, yeah, it is paused, would probably look something like this. Oh, excellent. So some of you have already seen CNC machines like in lab at Charlotte and stuff like that. Excellent. That saves a little bit of explanation. Yeah. However, CNC machines can be pretty big. Just to give you some idea of the scale there. They can, in rare cases, they can be even larger than this too. And basically, the whole idea is to be able to make, stuff. Yeah, you can. I'm sure you guys heard all about that. I'm sure you heard a lot about that. Um, oh, cool. Yeah, I haven't actually had the opportunity to see it, so I don't know myself, but that's pretty awesome if it is, because then you can do a fair amount with something like that. You can do something smaller, you can do something larger. It'll be able to um, do a wider variety of stuff. But yeah, the whole point of a CNC machine is to make more is to make very precise uh, sort of creations. Since it's all controlled by computer, there's a precision and an accuracy to it that you wouldn't really necessarily be able to get with manual lathes and stuff like that. Certainly you could once you got good enough, but there are always going to be weird tolerances and things like that when they're made by humans. Machines can help eliminate that those sorts of weird um, inconsistencies in manufactured items. Now, the whole point of a CNC machine is to remove material from a larger block of material, generally called a stock, in order to get the widget that you're trying to make. So it's what's called a subtractive process. You're taking material and you're removing stuff from it in order to get your final product, as opposed to a 3D printer, which would be like an additive process. You start with, sort of an empty board, and then you print stuff out on it. So you're adding material in order to get your final product. But yeah, um, CNC machines can be used to make a whole bunch of different stuff, including printed circuit boards, like a TARDIS. Yeah, the TARDIS can make stuff. None of these things are really bigger on the inside, though. They're pretty much the same size on the inside. That's the only thing. But yeah, so that's why we're getting you guys familiar with, all the CAD programs and stuff like that. And that's why we're going to spend some time going over circuit design with you guys as well, so that you can get familiar with it and learn how to, design a circuit and get it from, computer design to printed circuit board, so that you can make your own custom circuit boards. How many of you guys, show of hands, are familiar with printed circuit boards or PCBs? Got a few hands. Got sort of a wave going on. It was kind of great. Started at the top and then, yep. All right. So mostly everybody, but in case, in case you guys aren't really familiar, a PCB, or a printed circuit board, let's see here. Let me see if I can't pull up a... Well, that's good. That's very important. So here are 3 examples of a printed circuit board made in 3 different ways. Basically, a PCB is conductive material, like copper or whatever, generally copper, um, with a non-conductive material sort of laid over it. And is that right? I'm trying to think of the correct order here. Well, anyway, nice. Usually, there's the non-conductive material, and you etch away the non-conductive material, and then you dip it in some acid. No joke, you dip it in some acid. And then the acid will reveal some more of it and sort of clean it up, so that you've got bare copper underneath. And then you'll get something that looks like this. And it is, in essence, a quick way to make circuit boards. It's useful for, prototyping final products. It's useful for creating, hobby circuit boards for hobbies and stuff like that. Yeah, exactly. Not again. Not again. It's useful for a whole lot of things. Um, and it's rapidly becoming a, you know, a sort of widespread way to design circuits and test them out and things like that. So it's always good to get familiar with it, especially if you're interested in, electrical engineering or automation or things like that. You might, or robotics, you might, familiarize yourself with a PCB, get used to, making them and stuff like that, so that you can rapidly prototype boards. And automation, also known as Funimation. Also, that's the animation company. Could you make RAM? Well, okay. In theory, yes. However, here's the thing. The that was me. Um, the the thing is, computers are made up of millions and millions of yeah. So you're telling me there's a chance, millions and millions of transistors, which are basically just like little tiny things which determine which way electricity flows. And then the way that those transistors are set up can do things like logic gates, which are the way that computers think. You set up logic gates in specific ways, and you can make it do things like store information on it, or do addition. Well, eventually, yeah, potentially make nukes. Although we're gonna steer clear of that one. And stuff like that. So that's what RAM is made up of, just like the CPU is, just like a lot of the stuff on the motherboard. But like I said, it's a lot of transistors, and a lot of them are really, 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 really tiny. Like you can see them in a microscope tiny. And they're layered on top of each other. A lot of times, if you look at like a microscopic view of a CPU, let me just go ahead and CPU. Let me see. Let me find a good example. Yeah, this is a good example. Here's another one. Okay. Because I have lots of updates and they just pile on top of one another. My internet's so slow that like it pretty much takes up all of my internet in order to download any updates. So I just keep it paused. Um, these are what the transistors can look like on a CPU. This right here, this is 20 micrometers. A micrometer is I want to say 1/1000th of a millimeter. So this area from here to here is a micrometer, or 20 micrometers. Now, add to that they're layered in 3 dimensions. Let me zoom in so you can get a better idea of what this looks like. There are layers and layers of transistors and logic gates on top of one another in order to cram more onto the real estate that exists on a CPU, because you only have so much space. So you layer them on top of one another so that you can cram more onto a CPU. So between those two things, it's really extremely prohibitive to make, a PCB of RAM. Yeah, it's a lot. This is a CPU, obviously, which is not the same thing, but rest assured, RAM is also going to have a lot of logic gates on it. You might be able to make a single latch, and a latch, it's I believe a D-latch, which is the kind of logic gate that exists on RAM that allows you to store information. You can make like a single one, which would store 1 bit, and you could have a proof of concept of RAM. Well, I mean, technically, you would have RAM that would store 1 bit of information, either yes or no, 1 or 0, on or off. Um, so that could be pretty cool. But as far as making actual, yeah, exactly. As far as making actual usable RAM in like a computer today, mm, you can make a really big stick of RAM, like the size of a house, and probably it would be maybe a kilobyte of RAM, if that, and maybe a couple of kilobytes. And you can find some way to plug it in your computer. But as far as actually like today's RAM, we have the know-how. The process is not the same, but it's similar. So in theory, it's doable, but in reality, it's just too small and it's too much work. Although I like where you went with that. Anyway, back to the matter at hand. If we get you familiar enough with PCBs and circuit design, then potentially you could become a computer engineer in the future and design the next logic gate that could revolutionize storage on the computer, reducing the amount of size necessary in order to store more information and, just become absurdly filthy rich off of it. Yes, we are. Um, Gosh, interactive. So me and my friend had an idea. Could you have a massive amount of SSDs in RAID 0? Could you make RAM? Well, okay. Have you ever heard of virtual RAM? Okay, yeah, probably because that was in the days before we had gigabytes of RAM, gigs and gigs of RAM that you could just mess around with and use to your heart's content and used wastefully on the computer and stuff like that. Back in the day, back when RAM sticks were still measured in kilobytes and megabytes, when I was your guys' age, um, virtual RAM was a thing. So virtual RAM was where uh, basically it was when you were 56. Yes, when I was 56. I'm Benjamin Button. I age in reverse, um, and also really quickly. Um, no, actually, that's about no, that's his name. Yeah, um, but basically, they had this feature called virtual RAM, and it was a lot of times it was on like Mac computers and stuff like that. But you could find it, you could find programs for it on Windows and stuff. But it was like increase the amount of memory that your computer has. And what it did in essence is it allocated a part of the hard drive to act like RAM. So it would store information on the hard drive for programs and then pull it as necessary, and it would operate exactly like RAM. Now, here's the rub: access speeds. Yes, I am. Access speeds. I'm actually 29. For hard drives are incredibly slow compared to RAM. We're talking on the order of thousands, hundreds to thousands of times slower than access speeds on RAM. Granted, we don't really, I mean, we notice it, but it's not really something that we think about consciously. But like, if you were to take um, the time it takes to access something on RAM, process it by the CPU, and put it back into RAM, and make that be an hour, and you tried to do an equivalent sort of length of time for hard drive access speeds, you'd be waiting for a very, very, very long time for something to happen. Months, if not years, until the hard drive got back to you. So to answer your question, yeah, you could, but it's going to be really, really slow. It could be really big, though. But yeah, and in fact, there are temporary RAM sort of nodes on the CPU which are even faster than RAM, like way, way faster. Yeah, like 1,000 SSDs would give you a lot of RAM storage, but it would still be much slower than actual RAM, just because bus speeds and the access speeds aren't as much of an issue on SSDs, um, because they operate in the same way that RAM does. But the communication speeds between the SSD and the rest of your computer is much slower than it is between RAM and the rest of your computer. All right, so let's take a look at 123D circuit after that 20 minute tangent. Now, let me see here. Pull up 123D Circuits website. Well, I'm glad that at least given time you can figure out the difference between an apple and a banana. Or maybe not. Now I'm not so sure. Okay, so I placed a link into the chat box. That is 123D Circuits website. Now, your screen, when you first click on it, is going to be different from mine because I'm already logged in. So if I log out, yep, there we go. La la la. Okay, this is probably what you're looking at. Got it. So up here in the upper right-hand side, you can either sign in or sign up. If you guys have an Autodesk ID, so if you've used anything by Autodesk, you can sign in using that Autodesk information. If not, go ahead and click sign up and get yourselves a username and a password for 123D Circuits. Tinkercad is Autodesk? You're right, it is. I believe it is. So try signing in with your Tinkercad information and see what happens. Excellent. So it looks like Tinkercad, your Tinkercad login will work as well. Okay, so you might be looking at something similar to this. You've got overview, create, explore, learn, and shop, and then you've got some designs down here that other people are working on, and this is just some examples of some of the stuff you can do with 123D Circuit. You might not. But what we're going to do is we're going to create a new circuit in 123D Circuit. So if you go up to create, click that tab. Yeah, Super Sweet LED Chooser 9000. That is actually the PCB that you guys will make on Wednesday. I already did this with my high school class, so that exists. But if you click on Create, you've got Electronics Lab, you got PCB Design and Manufacturing, Circuit Scribe, and Mesh. For now, we're not going to touch the PCB Design and Manufacturing. We're going to get used to basically sort of the UI of 123D Circuit first. So we're going to do a new Electronics Lab project. So just if you click on Open Electronics Lab Hub. Oh, you don't see it? If you don't see the tabs up here, alternatively, you can click this little three bar thing in the upper left-hand side and click on Electronics Lab over here. Both will do the trick. So once you've clicked on that, you should be brought here to Overview, and then you've got, you know, New Electronics Lab up here, and then you might have this stuff down here, who knows. Okay, good. So once you've gotten here, click on New Electronics Lab, and we'll get it opened up. And it will think and download stuff and whiz and whir, and you'll get the little blinky dots, and it'll take a minute. But, well, what? Okay, there we go. You'll see this lovely digital breadboard right here. This thing is wonderful. How many of you are familiar with breadboards? Show of hands. Okay, some hands, but not a whole lot of hands, and certainly not every hand. So, a quick breadboard tutorial. Breadboards are very good for designing circuits really, really quickly because they're little, basically, they're just little plastic boards that have a bunch of conductive rails on them, and then these holes in the plastic. And all it takes is you just plug something into one of these holes, and it gets connected to that circuit. And you can just rip stuff out like really quickly. You could just be like, boop, pull it right out and switch it with something else if you wanted to. Like, it's really, really easy to work with breadboards. And the way they basically work, like if we were to pull off the top of the breadboard, you'll see that there are these rails underneath, which connect all of these holes to one another. And the design to them is it's a little bit weird to get used to at first, but it's actually not too bad. So in essence, I'm going to go ahead. Yeah, we'll just do this. You see these vertical ones right here. These are all connected. So if you plug anything into one of these, it'll be connected to any of these other ones. Now you might notice, so once you've logged in, on the upper left-hand side, you might see 3 bars. Go ahead and click on that, and then go to Electronics Lab. And then there should be a green button which says New Electronics Lab. Once you get to that screen. That help? No problem. Okay, so these are all connected. You might notice that there's sort of this big um, desert of plastic right here. This whole area separates these two sets of columns. So this area right here is not connected to this area right here. There is no connection between the two. Likewise, here is not connected to here, and here is not connected to here. And then the individual columns are not linked to each other either, so there is no connection between columns. This allows you to, help build circuits and things like that. It might make more sense once we start building a circuit, you can see the connections between the two of them. On the other hand, these horizontal ones, these are all connected all the way down. So you could plug something in at the top, plug something in at the bottom, or the left and the right, I guess, from this perspective, and they'll be connected to one another. They'll be in the same circuit. Now, granted, these rows aren't connected to one another, so there is no connection between the plus and the minus. But the entire minus row and the entire plus row, those are all one long rail. Same goes for the bottom down here. So it's a little weird to get used to at first, but it's not too bad. Once you get used to it, it makes a whole lot of sense, and it's actually really easy to work with. And the reason why these are all connected is to make your life a lot easier when you're hooking up power and stuff like that to the circuit. You'll see exactly why in a few minutes. Anyway, you'll notice that this breadboard has a blue outline around it. That is because it is currently selected. If it's not, you can just click on it and select it. You can click and drag with the left mouse button in order to move it around. If you click and hold with the right mouse button, you can scroll around the, basically you can pan your view around, and you can use the mouse wheel to zoom in and out. Pretty simple stuff, no real surprises here so far. Now, what I want to do is I want to rotate this breadboard so that it's in a more useful position for me. So what I'm going to do is I'm going to click on it, and I'm going to hit the R key on my keyboard. And as you can see, it rotates it about 30-ish degrees each time. Actually, probably 30 degrees each time. So I can spin it around like crazy, and if I hold down Shift and hit R, I can rotate it the other way. So anyway, I'm going to go ahead and keep it in this vertical position right now. So Now all of these connecting rows are horizontal, and then these connecting rows are all vertical. So we've just basically, kind of swapped it around so that it's easier to see. And that's generally more like, I guess, how you're going to view breadboards when you're working with them, at least in my experience. So that's why I'm doing it. You'll also notice up here, breadboard name 1. We can give it a more useful name if we want, um, or a less useful name. So we can call it the power. Oh, I can't. I can call it the PO. Okay, looks like I can't do that. Oh, no, it was just freezing on me. Added a light bulb, but it won't turn on. Aha! So you probably need to provide power to it. So let's go ahead and build our first circuit. It's just going to be a really simple circuit with an LED that lights up. So we're going to go to Components, and we got a whole bunch of different stuff down here. Resistor, LED, LED RGB, light bulb, 9-volt battery, potentiometer. Is that potentiometer? Power supply. The little webinar window was in front of it, so I took my best guess and it was wrong. AA batteries, coin cells, potentiometers, diodes, push buttons, slide switch, dip switch, capacitors, transistors, MOSFETs, Arduinos, Arduino micros, DC motors, um, microchips, micro servos, piezo elements, more breadboards, an IR sensor, a tilt sensor, just all kinds of stuff, like a whole bunch of stuff. But we're gonna, like I said, we're gonna go with a very simple design right now. So I want you guys to find the resistor and drag the resistor out into the white space over here. And then I want you guys to find the LED and drag the LED out into the white space over here. And then finally, I want you guys to find the 2 times AA battery and drag that out. So we just pulled out 3 elements: the AA batteries, the resistor, and the LED, or a resistor and an LED. You can just click away from the components tray in order to make it go away, or you can click it again up here on components to make it go away. Either one. But these are all the things we're going to need in order to make this little doodad here light up. Now, let's take a look at each of these components. Power provides power. It provides voltage and amperage, and it's really, not all that surprising and not all that, foreign of a concept. If you've ever used like an RC car before, you might have batteries in that thing that you either have to charge up, or it might be old school and have AA batteries. DS, Nintendo DS's, 3DS's nowadays have a rechargeable battery in them, but back in the day, the same way you can scroll. So if it's like a trackpad, you should be able to just stick 2 fingers on the trackpad, just touching the trackpad, and move your fingers either forward or back. Yeah, you. That work for you, Tim? Excellent. Yeah, for future reference, you can, if you didn't already know, you might have already known, you can use that in order to scroll on pages and stuff like that. Pretty handy. But yeah, Nintendo DSs nowadays tend to have rechargeable batteries, so you just plug them back into the wall. However, there is like a panel which you can pop out and pull out the battery and replace it with another one in case you need to, stuff like that. And then back in the day, the original Game Boy, the thing was like the size of a friggin' brick, and you'd open up the back and you'd have to put 4 AA batteries into it in order to provide it with enough power, and then it would run, like 6 to 10 hours on that amount of power, and then you would have to replace the batteries again. So like batteries were like gold to you at that age, because you wanted to make sure that your Game Boy still worked. So you just hoarded batteries like crazy. Awesome, nice work, John. But yeah. So that's how you provide power. Now, the LED obviously is pretty self-explanatory. Is that what I did? Yes, I hoarded batteries because my Game Boy, I had to play Tetris and Nintendo Tennis and Super Mario World and all that stuff, and eventually Legend of Zelda. Was it Link's Awakening? Yeah, Link's Awakening. Yeah, that was a good game. Anyway, um, oh, and Pokemon. I had Pokemon Red when it first came out, the original one. LEDs light up. LED stands for light emitting diode. Everybody should pretty much know this by now. Now, I don't still have it now. The thing that people might not be aware of is diode is another type of electronic component. No, I don't. I don't know any Pokemon since then. I've been wanting to get a Pokemon because it's been a while, but I don't know any. Um, hey, don't be hating. Um, Now, the thing to note about a diode is like a one-way street for electricity. Electricity can go one way, but it can't go the other way. Um, Going the other way, basically, the way it achieves this is like having sort of infinite resistance in the other direction, so electricity doesn't want to go the wrong way. But you want to make sure that your diode is hooked up properly, otherwise electricity goes the wrong way through the circuit. That the same goes for LEDs. It matters which way you plug in an LED. You plug it in one way, the circuit will work. You plug it in the other way, and you can burn out the LED. You can uh, burn some of the electrical components that you have. You can cause the batteries to overheat and explode in like really extreme cases, which is really super bad. There are a few bad things that can happen. So you always want to make sure that your LED is plugged in properly. And there's a way to say it. There's a way to tell. So usually LEDs will have like a notch on them to denote which side is which. Um, in this case, we can also look at the legs here and also mouse over the edges. So you notice that there's one leg that's bent, and then there's one leg that's straight. And if I mouse over it, it's labeled cathode. And if I mouse over the leg that's bent, it's labeled anode. So anode is basically the plus side of the LED. It's what gets plugged into the plus side of the circuit. Cathode is what gets plugged into the negative side, so it's the other side. Um, and unfortunately, there really isn't an easy way to remember that because it doesn't line up nicely with the easier way to remember anions and cations, but whatever. Regardless, that's just something you'll get used to as you get more familiar with LEDs. You might devise your own way to remember which one is which. Um, but yeah. And then you've got resistors. Resistors, well, resist the flow of electricity, basically. They slow down, for lack of a better term, the flow of electricity in a circuit. They take electrical energy and they turn it into heat energy. And this keeps circuits from doing things that are ostensibly cool, but not really in real life, like catching fire and electrical components exploding. Resistors are an important part of that. Otherwise, like if we just hook this up right now with no resistor, that LED would blow up. And it would tell us in 1, 2, 3D circuit with a little explosion thing on the LED. And that's, not ideal, but it could be worse. But anyway, yeah, I know. I've sent, I've started a few electrical fires in my day, and I don't necessarily recommend it, but it is a good learning experience. Anyway, let's go ahead and get started on hooking up our circuit. Now, if we look at the batteries, you'll notice that there is a positive and negative terminal. Red is positive and black is negative. This is also like ground and hot wire. Black tends to represent ground or negative terminals, whereas red tends to represent positive or hot terminals. Yeah, exactly. Um, with the really easy way to remember it, red means dead. A bit morbid, but um, it becomes something that's really important to remember if you start working on like really high voltages and amperages and things like that. Um, Certainly like home electrical systems and power generation and things like that. Although Unfortunately, home electrical systems don't really have a unified sort of wiring coloration. Sometimes green is ground, sometimes black is ground, sometimes white means hot, sometimes red means hot. So it's one of those things that you just need to get familiar with as time goes on. But for now, yeah. So what I can do is I can click on this positive terminal here. Nice, excellent work. I can click on this positive terminal, and then you'll notice that there is a line following my cursor, and I can click on the plus rail here. So I've just created a connection between the positive terminal on the batteries and the plus rail on the breadboard. So this whole rail right now is now supplied with power. Cool, so now we can draw from that anytime we need power. I'm also going to turn this line red so that we know that it's power. Just over here in this little menu, breadboard wire, you can change the color. I'm going to do the same thing with the black wire, run it over to the ground, the minus rail, and then change it to black so that we have a nice, easy color-coded way to tell. And I'm actually going to bring this, oops, down a little bit. There we go. Perfect. So now we got our power hooked up. Now anything that we connect to that will have power. Now for the LED, I'm going to go ahead and I'm going to rotate it to the side, like so, and hook it up along these two. Why should I do that as opposed to hooking it up like that? What's wrong with this right here? Well, I'll give you a hint. What are the rails doing? Yeah, essentially. So what's going on here is electricity is lazy. It always travels the path of least resistance, literally and figuratively. Um, it always travels the path that is the easiest for it to go, which means that if we were to hook up power to this and then, ground over here and complete this circuit, the electricity would come in and just basically go like woo, 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 and then keep flowing through the LED, increase the amperage and the voltage on it, and then pow, LED explodes. Because this would be the path of least resistance. It wouldn't go through the resistor, and it would just keep going through the LED until it eventually broke in some catastrophic fashion. So that's bad. We want to make sure that it bridges two separate rails so that we have a better circuit. So as you can see, we got the cathode and the anode here. I'm going to go ahead and hook up the anode to the positive power. So we'll make that red. I'm going to take this resistor and rotate it to the side and plug it in over here. And you'll notice that, the nice thing about a resistor doesn't care what orientation it's in. It does not have a polarity, unlike the LED. It can either go this way, or we can flip it around and put it in this way, and it's just as happy either way. Its entire point is just to turn electricity into heat, and it can achieve that with the electricity going either way through it. And that's all. Really easy in that sense. Now, what are these colored bands on the resistor? Does anybody know? Nice. I will. I will. We've got time. I just want to see if anybody knows what those represent. Okay, that's fine. The bands actually represent how much a resistor resists. Basically, the strength of a resistor is measured in ohms. The more ohms a resistor has, the more electricity it can resist. Basically, the stronger its resistance. Now, resistors, most resistors are about the size of a grain of rice, like really, really super small. So you're not going to be printing numbers on that because it's just too small to read those numbers. Um, the resistance, yeah. If I click on the actual wire itself, a little menu comes up over here on the right-hand side, and I can change the color of it. So I made it red just so we know that it's coming from the power. Yeah, exactly, Star Wars pun. But it denotes how strong a resistor is. So if we click on this resistor, we can see that it's 1 kilo ohm, so 1,000 ohms. That's what this brown represents. It represents a 1, and then this black represents a 0. And then the red represents how many times you multiply these first two numbers by 10. So in essence, it's like this. The first band is the first significant digit. In this case, it's brown, so it's equal to 1. The second band is the second significant digit. In this case, it's black, which represents 0. So now we've got 10. The third band is equal to 10 to the x, essentially. In this case, it's red, which is equal to 2, I believe. Yeah, it's 2. So this becomes 10 times 10 to the x. We fill the 2 in here, so it becomes 10 times 10 squared. 10 squared, as we all know, is equal to 100, which makes it 10 times 100, which is equal to 1,000. So just by reading the colors, we know exactly how much this resists. The gold band represents tolerance because it could be, it's meant to be 1,000 ohms, but it could be like 950 ohms or whatever, because manufacturing things and stuff. So if I were to change the amount of resistance here, let's go up to 100 kilo ohms. You'll notice that this yellow band changed color. If we go down to ohms, the band changes color again. If we change it to 35 ohms, you can see that all the bands changed color. Just all kinds of stuff. So we're going to make it 100 ohms, which I believe is the lowest it will go without exploding the LED. And then I'm going to click on Start Simulation up here in the upper right-hand corner. Click on that, and we see the LED light up. Look at that. If we increase the resistance, we can dim the LED more. So if we change this to 1,000 ohms, it's dimmer. 10,000 ohms, it's dimmer again. 100,000, dimmer still. If you click on Start Simulation up here in the upper right-hand side, let me just go ahead and circle it. It should simulate electricity flow in it. So that will light up the LED. You'll notice it gets brighter, and it'll tell you if there's anything wrong with the circuit. If you had other components, you could play around with those components and see, how they affect the circuit, things like that. For now, we just did a really, really simple circuit. It's just power to LED to resistor back to battery, and then, that's how we completed the circuit. So all it does is just lights up the LED. So I can click Stop Simulation and stop simulating. But yeah, and then of course, if we start the simulation again and I bring it down to 10 ohms, you can see there's this little explosion on the LED, which represents the LED would explode at that amount of resistance. Current through the LED is 54 milliamps, while the maximum is 20. So if let's see here, let's try 75. 75 actually is low enough. Cool. And so there are some other things we can mess around with. We can click on the LED and change the color of it, which is kind of cool. Totally useless, but kind of cool. Actually, that green LED was kind of nice. But yeah, this is just basically an introduction into. Oh, sorry about that. I was just going to say this is basically just an introduction to making things on 123D circuits. Certainly with the electronics lab, it's meant to simulate, real life breadboard use and stuff like that as much as possible. If you guys ever are interested in messing around with an Arduino, there's actually Arduinos in this mode. Oh, I didn't realize it still cut out. I apologize. There are Arduinos in this mode if you're ever interested in messing around with an Arduino. Not only can you, where is it? Where is it? There, nope, this one. Not only can you hook them up like you would a regular Arduino, um, there's also, see, like we've got, in fact, an Arduino Uno right here. So it's got all of the pins that a regular Arduino would have. Not only that, there's a code editor which simulates the code that you would put into an Arduino so that you can, do your own project with an Arduino. You can simulate it here in 123D Circuit before making it in real life, just to make sure that everything would work out. It's not lighting up. Check and make sure that your LED is plugged in properly. You want the power to be going to the bent leg on the LED. So you see how I've got the power running from the battery onto this rail, and then it's plugged in from this rail to the same rail that's on the bent leg on the LED. And then the straight leg is on a different rail, and it goes to the resistor, and then the resistor goes from this rail to the negative rail, which I have hooked up to the black terminal on the battery. So just, I guess, spend a minute making sure that it's all hooked up like that. Let me zoom in a little bit more so it's easier to see. There we go. This is more important about what's, connected to what as opposed to where it is on the breadboard. I can move this entire circuit down on the breadboard and it would still work, but you just got to make sure everything's plugged in. Okay, excellent. But yeah, like I said, just meant to be an introduction to 123D Circuit. On Wednesday, we will spend time introducing ourselves to the PCB mode and making a printed circuit board, at least simulated, on 123D Circuit so that we can export it to other plan and set it up so that, other mill could cut it out. You made a fan? Awesome. Excellent. But yeah, so let me just go ahead and I guess we'll do the poll questions now. We'll leave it open for question and answer time, do all that good stuff. Once the poll questions are done, if you have any questions, I'm here. If not, you're more than welcome to head out, and we'll see you on Wednesday. And we'll get started on PCB stuff. So let me go ahead and poll questions incoming.